Welcome to the third lecture that we have in Mathematics for Minor Finance. So today what we're going to do is have a look at differentiation. So if you remember from high school, differentiation having to do with the slopes of functions that are curvy, right? So general functions, how steep are these general functions? Well, differentiation is the technique that allows us to see whether, say, a function at some point is increasing or decreasing. And ultimately, we're actually going to use that also to figure out where a function attains its maximum or minimum, which is really important. So, and then I actually discuss some applications, and particularly today we'll go a bit deeper into increasing, decreasing a bit also convex and concave functions. So we'll see that later on in the second video. And then finally, we'll go through various calculational rules for computing derivatives, which is what you compute through differentiation of functions. So in particular, we'll have a look at the sum rule, the product rule, the quotient rule, and the chain rule for differentiation. But let's start with what is, again, differentiation. What does that mean? So here we have a couple of functions, or graphs of functions, rather, that we see here. So you see the purple line, the straight purple line, that's a linear function, right? So it's a straight line. So typically of the form, we saw this last time, a function f of x equals ax plus b, that's a linear function. It's a straight line which has some slope, and then we also saw that a actually measures this slope. So you can see this purple line down here having a positive slope. Okay. The dark blue line over here is, well, it's not a line, actually it's a curve. This is a quadratic function. So we already discussed as well last time. Quadratic functions have parabolas as their graph. So this is a parabola. So this is valley type parabola, right? So it has a positive coefficient in front of the x squared, if you wish. So you might be tempted to ask, so what's the slope actually of this parabola? And then immediately you realize, oh, well, that rather depends, right? It doesn't have a constant slope. It's sort of sloping downward on this side. It's now gets more or less flat over here, and then it's going to increase again. So just asking what the slope is not that well defined. But what we might be able to do is say, well, what's the slope at a certain point? So in particular, consider this particular point over here. It's 0.36. Apparently it's on this parabola. If I ask what's the slope of this graph at this point, well, you might actually at least agree with me that, it's downward sloping at this point. So what do we mean exactly? Well, what we might do, one way of defining the slope at this particular point here, is say, well, we might actually look at this light blue line, which is the tangent line to the parabola. So it touches on the parabola exactly in this point. Well, that's a straight line. So this light blue line has a certain slope, right? It's a line, right? With a slope. So what we'll do is we'll say that the slope of the parabola in this particular point, well, we'll identify that with the slope of the tangent line that's touching on the parabola in this point. In this case, that's the light blue line. So that slope actually is for any point a. So in this case, a would be 3. The x value at this point in the graph would be 3. The y value in this case is 6. Well, that's what the function maps to in this particular point a. So with p, in this case the point p, 3, 6 in this example, in general would be a point with coordinate x coordinate a, and the y coordinate, the height of this function, will be what this function takes a to if you apply it to a. So that's the y coordinate f of a. Now in that case, the derivative of f at this particular point, that's defined to be the slope of the tangent line to this graph at this point P. So in this case, this light blue line. We will denote that slope by f prime, so this little thing here is apostrophe, we call it a prime, f prime of a. Okay, so we're interested in the derivative, which means we're interested in the slope of the tangent line. So how would we determine such a slope of a tangent line at some point P? So I have a point P with an x-coordinate A, and then the y-coordinate is, well, function value if we plug in A for x, so f of A. And now here, it might be this point over here, point P, and we're interested, of course, in the slope of the tangent line, which is called here T in this graph, to that curve at P, the tangent line to the curve at the point P. So how can we actually determine this? Well, let me do that on paper, so to explain what this graph actually is doing. So let's go to the paper. So let me try to redraw that graph, more or less. So here we have the axis, the y-axis, and the x-axis. And we have this curve, right? It's the function. And we're interested in some particular point. This point, for instance, we call this x equals a, and then the y value of this graph is the graph f of x. The y value would be at this point f of a. We're interested in the slope of the line that's tangent to this curve at this point. So we're interested in the slope of the line that precisely touches on this point. What can we do? Well, so it's hard to figure out what that line is, but what we might do is say, well, what I can do, what's much easier, is draw a second point, say, for instance, this point, and draw a line that connects those 2 points. It's of course the wrong line, right? It's not the tangent line. It's a different line, but we can compute its slope. So this line, let me call it L, so the tangent line will be this one. The line L, which you also have on your slide. Of course, actually, so on the slide, this point is called P, this point is called Q, so you can look that up later. We can actually compute the slope of that line. So that we make this same picture, but with a bit less notation. So we have this graph, and I'm interested in this point P. I'm going to choose the point Q. And now, instead of asking what's the slope of the tangent line, I'm going to ask what's the slope of this particular line. Can I compute that? Well, yeah, basically I can, because I know 2 points on this line. So the first point is the point with x value a and y value f of a. So the first point P on this line is of this form, a f a, so x value a, y value f of a. This point Q, I took it a bit to the right. So how much to the right? Well, let me say I'm going to choose the x-coordinate for Q to be a distance h in terms of horizontal movement away from A. So it will be at the point A plus h. So what's the coordinates for Q? Well, the x-coordinate for Q is A plus h. Do we also know the y-coordinate for Q? I guess so. It's on the curve, right? It's on the curve for F. So its height must be F of A plus h. So I have 2 points. I have a line connecting those 2 points, or going through those 2 points. It extends beyond this line. It's an infinite line. I'm interested in what's the slope of this line. Well, we covered that actually last time, didn't we? In the case of the linear example, we figured out what the slope is of a particular line if you know 2 points on this line. So what was that again? What did we have to do? We had to look at the delta y, the change in the y-coordinates, the vertical movement as you move horizontally in the x direction from a in this case to a plus h. So the slope of that line connecting P and Q was basically how much vertical movement do I make as I move in the horizontal direction. How much is that? Well, we can use that, right? So we know what the vertical movement is. It's f of a plus h minus f of a. That's the difference in the y-coordinates. And I have to divide that by the difference in the horizontal direction. So it's a plus h minus a. Essentially, that's of course just h, right? So the movement from left to right, from a to a plus h, is exactly h. So this expression actually measures the slope of the line between P and Q. Was that what we were interested in? No, it's not, of course. We're not interested exactly in this line L. We are actually interested in the slope of the line T, the actual tangent to the graph at the point P. But now you might notice, I chose this point Q fairly arbitrarily, somewhere to the right. I could have chosen it a bit closer. Perhaps I could have chosen it over here. Or I could have chosen it over here, still a bit closer to P. And as I get closer and closer to P, so as the point Q that I chose at random essentially gets closer and closer to P, you'll see that the line that's connecting P and Q gets closer and closer to this tangent line that's actually touching on the curve at the point P. So what is now the slope of the tangent line? Well, it's actually the slope of this line connecting P and Q, provided that I take Q very, very, very close to P. So how would I define very, very close? Well, I just want to make sure that this h, this horizontal movement, is very, very small. So I'm going to define the slope, the derivative, the slope of the derivative at P. So that is, by definition, the slope of the tangent line. We call that T, the tangent line. It's going to be this object here, so the slope of that particular line, Fa plus h minus Fa divided by h. But as I choose this h very small, and we denote this in mathematics as the limit of if we take h as small as possible, so going to 0 essentially. So the slope of the tangent line is just the limit of this expression if we take h small enough. Okay, let's see how we can make that operational. So we are on the slide. So again, we had the points P and Q. So I could compute the slope of this line connecting P and Q. So I know the horizontal direction is just h. The vertical movement is f of a plus h, which is the y-coordinate for Q, minus f of a, which is the y-coordinate for P. So I can actually compute the slope of that particular line connecting P and Q. So here I did this actually. So it was this expression here. And what I now want to do is I want to pick this h as close to 0 as possible. So if I take this this h, this horizontal movement really small, or in other words, if I take the limit as this h goes to 0 of that particular expression, that by definition is the slope of the tangent to f at p, or in other words, the derivative of this function f at the point P, or at the x-coordinate a, if you wish. So can we use this? Well, let's use this, try to use this in an example. So suppose we have a certain choice for this function f. So let's look, for instance, at an easy one. the quadratic function fx equals x squared. So the simple quadratic function. So let's just do the computation that we want to do and see what it works out for if we take this particular choice for f. So let's do that again on paper and then we can see it again on the slide. So suppose indeed the function f now, f of x in particular, would be x squared. Now I want to compute in the point A the derivative f prime in some given x equals a. So f prime again, that's the derivative in the point A. If I take as my x coordinate the number a. So let's use this expression here. It's defined as the limit of this horizontal movement h being smaller and smaller of fa plus h. Well, let's just use the fact that we know f of x is x squared. Then what's f of a plus h? It's just a plus h squared. That's a y coordinate at the point Q if you wish. And the y coordinate at the point A itself, the point B, is just h squared. And I need to divide this by h. Okay, does this help? Yeah, sure it does, because we can actually work out this expression here and learn something. So a plus h squared a plus h squared, that's actually h squared, of course, plus 2ah plus h squared. So let's plug that in. So f prime of a equals h squared. I'm going to write down a plus h squared, this expression, h squared plus 2a times h plus h squared, right? This was essentially, you recognize here the quadratic identity that we already identified in the first lecture. So that's this bit here. I have to subtract from that minus a squared, and I need to divide by h, by this horizontal movement, h. Okay, something nice is happening here because these a squared terms are cancelling, right? So this says only stuff that's left is this bit in between here, 2a times h plus h squared divided by h. If you're watching carefully, you might have seen I forgot to write down we need to take this limit, so let me do that. So let's go on here. This numerator I can factor out in h, right? There's a common h in both of these terms, so let me just write this as h times 2a plus h, right? So h times 2a gives me the 2ah, h times h gives me the h squared, and I need to divide this by h, still the limit. Still interested in limit h going to 0, but now see h and h occur here in the denominator and the numerator, so I can divide those out. So it's the same as this limit 2a plus h. Well, now I can take the limit. What's 2a plus h if I take h and a smaller and smaller closer to 0? Of course, that's just, can just plug in h equals 0, 2a. We'll get closer and closer to the value 2a. So what have we learned? If the function is x squared, so our f is f of x equals x squared, then I can just do the procedure that I just discussed, plug this in, take the limit, and find out, oh, actually the derivative of f in the point A is 2 times a. So let's go back to the slide. And that's actually happening here. So what we're doing is we just use this definition. In the slide, actually, the a is just called x, which is fine too, of course, just a name. F prime of x was this limit of this difference between the f and the 2 points divided by h, and limit for h going to 0. I use this getting the fact that f is this quadratic function, fx is x squared, and I'm getting rid of some of the brackets to figure out actually that you can get rid of the h in the denominator here by dividing it out, 2x plus h, and then this limit ultimately, if I take h small enough, reduces to just 2x. So the derivative of the function fx equals x squared is actually 2x. And that might be something that you recall, or that you have learned, have seen before in high school, I guess. So the derivative of x squared is 2x. We can do this more generally for any power function of x. So say x to the power a. So a might be 2, then we would have x squared, but might also be 3 or 4, or perhaps even minus 1 or minus 2. So if f of x equals x to the power a, where a is some constant, then how do we compute the derivative? Well, the trick here is the rule. What we're going to do is just take this a, put it in front, as this one, and lower it by 1 in the exponent. That's basically the outcome of doing the procedure that we just did. So we just looked at the case where a equals 2, so we had x squared in that case. What's the derivative? Well, take the 2 in that case, put it in front, so we get 2x to the power 2 minus 1, which is just 2x to the power 1, 2x. So this is a general rule. We can derive it once, but once we know it, we can use it all the time. So in practice, actually, what we did here was the definition, but once we know what the outcome is of that definition for these power functions, we are done and we can actually use that. So what we do in practice, when we encounter a power function, we already say, oh, wait a minute, I'm not going to do this whole limit procedure. I know what the derivative of a power function is. Namely, what I need to do is I take the power, a over here, put it in front of the expression and lower the power or the exponent by 1. That's how it works. So let's look at a couple of examples. So if my power is 3 over here, so fx is x cubed, or x to the power 3. What's the derivative? Well, what do you need to do? I take the power, the 3, I put it in front, and I lower the power by 1. I get 3 times x squared. I can also do this with non-integer powers. So remember the cube root, the third root of x, we can write this also, it's also a power, right? It's x to the power 1/3. The meaning of x to the power 1/3, that's just the third root, or the cube root of x. Same form as this one. So what do we need to do? Well, if I want to take the derivative here, what do we need to do? I take this power, the 1/3, I put it in front, 1/3 gets here in front, and I lower 1/3 by 1. So what's 1/3 minus 1? Think about it. It's actually minus 2/3, right? 1/3 minus 1. I want to convince yourself that this is actually minus 2/3. Okay, let's look at the final example. So this looks complicated, right? So there's a lot of power functions. But we can actually simplify this in just a single one, because what this basically says, it's x to the power 1 divided by x squared. Well, x divided by x squared is actually x to the power minus 1 divided by the square root of x, but the square root of x was x to the power a half, so I have to subtract once more a half from the minus 1 that we had. So if I add up or subtract all the powers, we end up with the fact that this is x to the power minus 3/2. So all these powers together are actually working out sums and difference of the exponents or the powers, ends up being the same as x to the power minus 3/2 or minus 1/2. So once we are there, what's the derivative of this function? Well, again, same recipe. We take the power minus 3/2, put it in front, here it is, minus 3/2, and then look at x to the power, well, 1 lower. So what's minus 3/2 minus 1? It's minus 2/2, right? Or minus 5/2. So this is the resulting derivative here, minus 3/2 times x to the power minus 5/2. So that's all those three examples are applications of the general rule. If I have a power function, taking the derivative just means putting the power in front and on the x reducing the power by 1. That's what we did in these three examples. So let's have a look what it means also for a constant. Well, actually nothing new here. One example that I didn't do is take x to the power 0. So what's x to the power 0? If a equals 0. Well, something to the power 0 is always 1, right? So x to the 0 is 1. So even the function fx equals 1, that's a power of x, named x to the power 0. Well, let's apply the same rule when a equals 0. A equals 0, so I put the 0 in front, times x to the power minus 1, but 0 times x to the power minus 1 is actually 0. So the derivative of the function fx equals 1, which is the same thing but with a equals 0, this derivative is actually 0. We have that here, a constant function. Well, fx might be 1, it might also be constant but a bit higher. So this capital A over here might be some constant value. The derivative of a constant function is always 0. And that makes some sense, right? So as I introduced derivatives, I said, well, it's actually the slope of the line that's tangent at this particular point. Well, for a constant function, that is already a straight line, a horizontal straight line actually. So what's the slope of a horizontal line? Well, wherever you are on this line, if it's flat, it remains flat, and the slope is actually 0. So this makes sense. So the derivative of a constant function, whatever its height, capital A over here, is always going to be 0. So particularly if, for example, if fx equals 5, whatever x you put in is always 5. You always get a y value of 5. So we'll have a function which is flat at height 5 for whichever x you put in. Well, it's a flat function, so slope will be 0 everywhere. So the derivative of this function is going to be 0. What we can also look at is, suppose we have one given function f, so this wavy red line would be the function f, and it has a particular derivative, which would be the slope of the tangent. So particularly in this point, it would be the slope of this upward sloping line, this black line. What happens if we define a new function, let's call that g, which is a bit higher? So it's, in this example, would be fx plus 2. So it just shifted up, same function as the red one, but shifted up 2 units. So gx is just same as fx, but shifted up, in this case, a units. And for the picture, a was this big, a was 2. Well, then we know that if we look at the same x coordinate, actually the slope of the tangent line, or in other words, the derivative, is actually precisely the same. So if I take the derivative of a function plus a constant, that's just the same thing as the derivative of that function itself. So the constant basically vanishes upon taking the derivative. So here's an example. Gx is x squared minus 13. Well, that's first thing is power function, x squared. We can take the derivative of that. We already saw before the derivative of x squared. That is 2x. But now looking at x squared minus 13, so it's a bit lower than that. Gx is x squared minus 13. The only difference here is this constant, the minus 13. I'm shifting this function down by 13 units essentially. Upon taking the derivative, g prime, this constant really doesn't matter, it drops out. So still the derivative of g of x will be 2x. So what happens if I multiply a function by some constant? So here I define the new g of x by multiplying the old f of x by, again, a constant, a capital A. So here we do this for a picture. So again, we have this wavy line, the red line, which is a graph of f of x. The green line is the graph of 3 times f of x. So wherever f is 0, which is over here, that's actually, it will have the same height. But here the height is multiplied by 3, so it's a lot bigger. And here the height is also multiplied by 3. It's below actually the x-axis, so it's going further down, right? So just a multiplication of the original function. Can we compute again what the derivative is for a function multiplied by a constant, capital A? Well, the derivative of this g is precisely the same as the derivative of the original function f, but again multiplied by capital A. So if you look at these two lines, which are the tangent lines at that similar point, the slope of this tangent line to g is precisely, you might imagine, 3 times as big as the slope of this tangent line at the same x-coordinate to f. So let's take again one example. So if g of x is 4 times the square root of x, well, what's the derivative of g? We'll take the derivative of the square root of x. What was square root of x again? It was x to the power a half, right? So this derivative of x to the half is a half times x to the power minus a half. But this constant that multiplies the square root of x here just continues to be present in the derivative, continues to multiply the derivative. So it's 4 times this half times x to the minus half. And if I work this out, 4 times a half gives me 2. And actually a different way of writing x to the minus half is 1 divided by x to the half, or 1 divided by square root of x. So g prime in this case will make 2 divided by the square root of x. So try this yourself, just to make sure that you understand what's going on. A final note here, I guess, is on notation. So how do we write, how do we denote a derivative? So if you have some function f of x, or sometimes you call this then y, right? The height of the function is y, it's f of x. Then there are actually different kinds of notations for what we mean by the derivative for this function that we will encounter in practical assignments. So I already covered this f prime of x, right? That's the derivative of f. Sometimes we like to call it dy divided by dx. So this d originates from this, essentially from this delta, right? The difference between the y values divided by the difference of the x values. So dy divided by dx. And we also sometimes use the notation d of fx divided by dx. And sometimes we write this d divided by dx just in front of the f of x. And occasionally you even see the notation y with a dot superimposed on it. So a dot on top of it, y dot. We won't have that much in this course, but you'll see it in some courses in your master's degree, perhaps. So these are all different notations for actually the same thing. They're all notations for the derivative of this function f of x. Okay, so let's go to the next video where we'll have a look at some applications of differentiation and derivatives.